So in the last class we have started discussing about the advanced surface characterization techniques, and I have introduced to you the subject, given different examples from our own studies showing the importance of the surface characterization techniques from the perspectives of material science and engineering. So we need to now go into details of each of these techniques. The first one which we will discuss is X-ray photoelectron spectroscopy, or what is known as XPS in the literature. Many of these slides which I am going to show you can be actually seen in this first book, which is by Terry Burr and published in 1994, but in the encyclopedia also you can get a lot of information. First one is, what is XPS? XPS, as I said, it is known as X-ray photoelectron spectroscopy. That means you have X-ray source and photoelectron as the output. That's very clear, is it not? So what is actually done? As you know, photoelectric effect was discovered long back, almost like 90 years back by Sir Albert Einstein, and he received a Nobel Prize because of this discovery. In the photoelectric effect, normally if a photon of certain energy, suppose h nu, falls on a photoelectrically sensitive material, the photoelectricity is generated because of the production of electrons. That is what is shown in the first slide. You see there is a light source with energy of the photon quanta, which is coming as energy of h nu, and this can actually eject out electrons from the photoactive elements, and that can produce electricity. Fine. So that same thing can be used to make photoelectron spectroscopy. The source which can be used in the photoelectron spectroscopy is not the photon but an X-ray. So this was done by K. Sackman and he received Nobel Prize after 60 years of Einstein's discovery. Both of these two scientists are from Germany, and Sackman received Nobel Prize in 1981 for the discovery of this. So what is done here? You have an X-ray photon coming from an X-ray source. It can be any actually X-ray source like copper or nickel or chromium or iron, and this X-ray photon falls on a certain, suppose, molecule. Here is an oxygen or certain atom, actually oxygen atom, and then because of its high energy it ejects one electron from the inner cell, that is 1s cell of the oxygen atom, and this electron comes out. This electron is basically oxygen 1 electron, photo ejected electron, and we can use this electron to study different kinds of behavior, different kinds of aspects of this spectroscopy. That is what is the basic principle of the technique in a nutshell, what I can say you. So, and as I said in the last class also, this is known as ESCA, electron spectroscopy for chemical analysis, but it has different acronyms like XPS, X-ray photoelectron spectroscopy, or UPS if you use ultraviolet as a source of energy, ultraviolet photoelectron spectroscopy, or you can use a photo light like photo, so which can lead to emission of electrons, then it is called a photo emission spectroscopy. But we are going to discuss these two mainly. So we are not going to discuss what will happen if you use ultraviolet or photon light actually and then produce spectroscopy. Well, what is actually the process? What is actually the analytical methods? Let us show it in terms of energy diagrams. What I am showing here is basically energy levels of certain atom. You can see 1s, 2s, 2p, 3s like that. So 1s has 2 electrons, 2s has 2 electrons, and then 2p has 6 electrons in the shells. So then you have 3s which is unfilled, and then you have valence band. After that you have a Fermi level. So, and below Fermi level actually all the specified levels of the energy levels are occupied by atoms, electrons sorry, and then you have EV, at a higher level, then basically EF by difference of phi is known as work function, as you know that from the Einstein's theory. So this is what is called kinetic energy, this is what is called binding energy. Now if a photoelectrons or X-ray actually comes and falls on this atom and it ejects, suppose one of the electrons in a 2p shell, and this electrons then has sufficient kinetic energy to travel to this valence band and even pass the Fermi level and come out, this is known as photoelectron. So we can calculate the kinetic energy of the photoelectron as h nu, which is the incident energy of the photon, minus EB, EB is basically the binding energy, plus phi is the work function. So this is work function, you know, and EB is basically binding energy. That is how we denote. So that means the binding energy is the energy with which this electron is bound to the nucleus. So that means XPS spectrum basically can always plot the energy or the intensity of the photoelectrons I versus either the binding energy, that is EB, or the kinetic energy. They are related, as you can see. Phi is, that is work function for a material, is well known. H nu is the energy of the incident X-ray, that is also well known. So therefore the two things which can vary is the Ke or EB, depending on which atom, which electron you are ejecting out. So that is why the XPS plots basically will be intensity versus either EB, that is the binding energy, or kinetic energy. That is how the plots are made. Now what all we can do with this? This is basically the principle which I told you, that is how things are actually happening inside a material. And as you know, why it is called surface characterization tool, as you know, this electron, photoelectron which is coming out from the sample will have energies, something kinetic energy not very high. So therefore if it is ejected deep inside the sample, then this electron may not be able to come out from the sample surface and we cannot analyze. That is why we use surface actually characterization, this technique is used for surface characterization tool. Now what all we can do? We can do elemental identification, obviously, because we know what is the exact energy of the electron which is coming out. So we can categorically say which element is present. We can actually even tell chemical state of the element, that is whether it is a oxidized, reduced, what kind of state it is, or it is a neutral. We can actually measure the relaptic composition of the constituent in the surface region, and we can actually obtain valence band structure. In fact nowadays we can actually do mapping of different elements present on the surface, in the surface. So therefore lot of things can be done in the XPS, that is why XPS is considered as a versatile tool. Now before I get inside into the other things of XPS, let me just explain a little bit about what is Auger, because Auger is also used in the purpose. Let us see what can be done in Auger. So this is what is this. The first picture is basically correspond to the XPS, as you see K electron, K's level L1, L2, 3m, then the Fermi level, then the vacuum level, that is EV, and these two are differentiated by work function. Okay, so now an X-ray falls and eject electron comes out, this whole thing is known as XPS, right. Now in this case, the last picture, the last basically schematic diagram, what is happening? If you see, if this becomes vacant by ejecting the electrons out by the X-rays, and higher level electron, higher level means suppose at L1 level electron can fall back into the K level and thus releasing certain energy. When this comes to this, some energy is released, and this energy then can be used to knock out an electron at a higher, much higher energy level, that is L2, 3. This electron will have sufficient, a little bit of kinetic energy, not as high as the XPS electron, X-ray photo ejected electron, but it will have certain energy. This electron is known as Auger electron. So therefore, in a nutshell, I can say Auger electron production is totally different from the X-ray photoelectron spectroscopy. Here basically jump of the electron from a higher level to lower level leads to production of certain other energy h nu 1, which can basically eject another electron from L23 cell, and that electron comes out from the sample surface is known as Auger electrons. So obviously the kinetic energy of this Auger electron is much lower than the XPS. That is why Auger spectroscopy is always done from the region near to the sample surface. You cannot actually probe little inside the sample surface, while the XPS can be used to probe the sample surface which is deeper compared to Auger. So that is why XPS and Auger, these are complementary tools, very widely used. Remember, Auger was discovered by Auger, so that is why this process is named after him. We are going to discuss this Auger spectroscopy in detail, so let us not talk about this right now, but for the sake of your understanding I am just going to tell you what is Auger spectroscopy. Now let us go back to the XPS again. In XPS, binding energy reference is done like this. Let us do that. Suppose this is a sample, they have a core electrons, then you have binding energy. Binding energy means this is what the electrons are there. Then this is as a Fermi level, as I said, EF, and there is a work function. Then you have a vacuum energy level. Okay. So once the X-ray falls, it basically crosses the binding energy, then Fermi level, then this work function comes out. That is how actually you get kinetic energy of the XPS as this h nu minus BF minus phi of the sample. So and that is basically then if in a case of spectrometer, what happens? There is a vacuum level, then there is a spectrometer work function. So this needs to be subtracted. So basically it depends, the kinetic energy is basically when this comes to the electron falls on a spectrometer, kinetic energy becomes like this h nu minus BF minus phi spec, because Q sample, phi sample basically cancelled out. So finally we get binding energy is basically equal to binding of the electron, h nu is the energy of the incident photon, the X-ray photon, minus the kinetic energy minus the phi spectrometer. Now as you know, this is fixed, well known in a very particular spectrometer. This is the fixed also because we know what is the incident energy of the X-ray. So basically what is varying is this and this, or these two are dependent. So now we can actually calculate, if I know this, the kinetic energy, or if I know the kinetic energy, we can calculate binding energy. Basically what we measure is the kinetic energy of the electron, and that can be used to calculate the binding energy which is present in the electron. So that is how actually we can characterize the electron which is ejected out. How the instrumentation is done we are going to discuss in detail later on, but to show you that, so what we have is basically you have a lot of different stuffs are there here. This is the basically heart of the system. You have a sample, you have X-ray gun, and you can have electron gun. Basically X-ray has always an electron gun, and then you have an ion gun to basically clean the sample surface. Many times you can use argon ion because this is done inside a vacuum chamber. So once the electron are ejected, this passes through this electrostatic transfer lens. This is what is shown you here, and then it basically goes through a hemispherical portion and then falls on the electron electron multiplier, which is nothing but basically a gate, and then it is getting amplified the signal through when it passes through this multiplier, and then it is recorded after it passes through a red meter, it recorded, and we get a plot between intensity versus kinetic energy or intensity versus binding energy. That is what is shown you here. Well, that is actually simplest possible thing, but it is not so. Then you have a control unit, and there are many other stuffs related to it, but this is what is done. Remember, it is done in a very high vacuum system because electrons needs to travel through this. That is why we need a very high vacuum system. Vacuum level should be 10 to the minus 9 torr, and we need also any kind of surface contamination or the surface reactions. So that is why X-rays energies which are allowed to fall on the samples should be tailored so that there will be no surface reaction or contamination formed because of the X-ray falling on the sample surface. Well, let me show you a typical X-ray XPS spectrum. I am going to show you two spectrums, one from our own, other ones taken from the literature. As I said in the last class, we have been working lots on the hydroxyapatite and hydroxyapatite metal, that is titanium composites. So from the surface, the spectrum is taken both from hydroxyapatite and hydroxyapatite titanium composites. It's basically intensity versus binding energy plot. Intensity is in arbitrary units, that is called basically the energy, the number of counts, CPS, sometimes we call CPS, counts per second, and binding energy is always written in units of electron volts. So as you see, we can see different peaks. As usual, any spectroscopy have a background and a peak, okay, and the most intense peak coming from both the sample is oxygen 1s, for which I have already discussed with you. Then you have a peak coming from carbon 1s, which is basically used as a standard in a XPS, because you know all samples have some common carbon. So you are going to see these peaks. So many times the spectrometers actually are basically calibrated using this peak position. Then because it's a hydroxyapatite, hydroxyapatite formula of Ca10 PO4 whole 2 OH whole 2, okay. So as you see, there is phosphorus, there is calcium, there is oxygen, there is hydrogen. Hydrogen normally not detected, and you see oxygen peaks, calcium peaks is here, calcium 2p 3 by 2, calcium 2p half. We are going to discuss what is the meaning of that. These are present both in hydroxyapatite and titanium. Then you have phosphorus peaks P2p and P2s coming in this positions, and altogether you have basically little bit of titanium peaks here. You can see carbon 1s and carbon 2s will be present always. This titanium peak is not visible here, but little bit small peak is visible here. So that is how we can say titanium is present, but basically titanium is not present as a metallic state, it is present as a oxide state or basically oxidized state. So that is actually how this XPS spectrum looks like, and we can analyze different things from this. We can calculate the element present, the chemical state of the element present, and we can calculate the percentage of the particular element present by calculating the area under the peaks. We can calculate in fact the chemical shift because of the binding of the elements with any other things. Lot of other things can be done, which is the part of the topics of this lecture. Typical XPS spectrum for indium phosphide 110 surface. As you see here, you see only indium and phosphorus peaks. You see indium 3s, indium 3 1 by 2, this is 3p 1 by 2, this is 3p 3 by 5, 3d 3 by 2, this is 3d 5 by 2, okay, this is 3 by 2. This is phosphorus peaks will always have a high binding energies when the indium, as you know. Phosphorus 2s, phosphorus 2p, indium 4p, indium 4d. So indium has 3s, 3p, 3d, 4p and 4d. Phosphorus has 2s, 2p peaks, which is clearly detected, and then you have a background in this. That is how actually the peaks, the spectrum looks like. I hope things are clear in your mind how XPS works and how the spectrum looks like, because we are going to use this spectrum. Now to give you more idea, let us look at a very high atomic number elements like uranium and talk about binding energies and the ionization cross sections. This is binding energy versus ionization cross sections. As you see here, different kind of energy levels are there. You have 4p 2 spins 1.5 and 3 by 2, 5d 3 by 2, okay, 5d 3 by 2 is small also there, and this is different. Then 5p half, 5s and 5d. On the other hand, f levels are there also, so f 5 by 2, f 7 by 2. You can see the ionization cross sections are very high. Ionization cross section means how much electrons are created after you ionize with these X-rays. Very high for 4f electrons, followed by 4d, then 5d and 4p. Other ionization energies are very low for these electrons like 5d, 5p and 5d and 5s, because they are very close to the Fermi level. So that means the electron yield, photoelectron yield by X-rays, X-ray spectroscopy will depend on this ionization cross section. That means this will be higher for these energy levels for case of uranium than others. So that means we can do such a kind of analysis for all elements and then figure out whether this actually happens in a particular system or not. Well, now let us get into nitty-gritties of that. As you see, for P, D and F peaks, there are always 2 peaks are observed. Here you see for gold 4D 3 by 2 and 4D 5 by 2. Please, that means D peaks are actually comes as a doublet. Separation between these 2 peaks are named as a spin orbital splitting. The values of the spin orbital splitting of a core level of an electron in different compounds are nearly same. You must remember this is very important. That means values of the spin orbital splitting, this is the spin orbital splitting value, this is for a core level electron in different compounds are nearly same. Peak ratios, peak area ratio, that means this is the peak area for these 2 electrons. Peak area ratios of a core level of an electron element in different compounds are also nearly same. These 2 are very important. Now I have not discussed what is the spin orbital splitting, I am going to do that, but this is what we observe and we have seen some of these patterns. The spin orbital splitting and the peak area ratios assist in elemental identification. Okay, now let us look at what is it. What is spin orbital splitting? This is first to tell you how actually done. Electron has a up spin or down spin. It is half, minus half, plus half. So what do we do here? Basically we use something known as ALS coupling. We do not use only S. As you know, the principal quantum number N, L, S, all these things you are very aware of it. So L and S actually talks about the spin of the electrons. So here we are using L and S coupling. So this number J is what is this number 3 by 2, 1 by 2 is basically L plus minus S. As you know, S can be either plus half or minus half depending on the spin. So if you have this kind of situations, one up and down, so one is up is called plus half, down is called minus half. So in this case when is up it's basically J equal to L plus half. If it is down, the J is equal to L minus half. Okay. So first one, the way peaks are noticed is first is the principal quantum number 2p. Okay. As you know, 1, 1s, 2s, 2p, 3s, 4p. That's how the principal quantum number actually goes. So first digit in the peak notation is corresponds to n, the principal quantum n. Second one corresponds to L, the magnetic quantum number, that is P, S, D, F. There are 4 sets as you know, and so that means S is equal to what? Is basically S is equal to 0, P equal to 1, D is equal to 3, F equal to 3. D equal to 2, F equal to 3. So that means P is equal to 1. So it's 2 corresponding to n, principal quantum number n, P corresponds to what? 1. Then if it is 1 plus half, the electron is up spin, then it's positive, so it's become 1 plus half equal to 3 by 2, correct. So that is what is shown here. When L equal to 1, that is for P cells, either it is P 1 by half or P 3 by half. If it is P 1 by half, that means P 1 minus half, 1 is basically L and minus half is basically down spin. So that's what is that, and then here it is P 1 plus 1 half, that is 3 by 2. So 1 is corresponding to the L, P equal to 1, that is this magnetic quantum number, azimuthal quantum number, not magnetic quantum number, sorry, azimuthal quantum number, and half is basically coming from up spin. So it has been found that area ratios, that's what have been discussed, of these 2 peaks will be 1:2. That means 3 by 2 will be double area, having double area than the 2. Now D, will D correspond to L equal to 2, right? So if L equal to 2, so that means D, it will be 2 minus half, that is D 3 by 2, where minus half is corresponding to down spin, right? And otherwise it will be 2 plus half, then half plus half corresponding to up spin. This is how actually we are designating area ratios of these 2 spin orbital splitting is 2:3, and then F correspond to L equal to 3. So L equal to 1 for P, L equal to 2 for L, PD, and L equal to 3 for F. So as you see, 3 minus half will be 5.5. So that becomes downspin electron, and 3 plus half will be 7/2. That's will upspin electron. Area ratios of these two peaks after splitting will be 3:4. So in a nutshell, this slide is, that's why it's very important for you to understand. In a nutshell, we can actually obtain spin orbital splitting information in XPS, and this is how things are designated. This is how things are actually, peaks are marked in the XPS spectrum. Now let us look at how we can use this for gold. Gold has it has 4s, 4p, 4d, 5s, 4f, 5f, and 5p electrons. So what are they? The binding energy for electron is 763. This is what is there, 763. 4p half, that is downspin, is basically 643. This is the one. 4p 3/2 upspin, it is 547. You see the area ratios are 1:2, this is 2:1. Then 4d, you have a 3/2, that is downspin. This d is corresponding to 2, L equal 2, so therefore L 2 minus half is 3/2. This is what is that. This is coming around 353 electron volts binding energy, and 5/2 will come 335. They are very close by. Area ratio is about how much? It's about 2:3. Now if you look at 4f, so 4f has 88 and 84 as a binding energies. This is the one, this is the one, very close by, 88, 84. So 5/2 is 3 minus half downspin, and 7/2 is 3 plus half upspin. Area ratio is 3:4. Then you have 5p, and others many times are not observed. 5f and 5p is 5p is observed, 5f is very close, so it is not observed, but not seen. Now we can actually use this area ratios for quantitative analysis. That's what was done. In this case, we have used aluminum K alpha as a X-ray source. So in case of Auger, if you look at it, the binding energies for say, I am not discussing here, but I will discuss later, is N0 is 1116 electron volts, N5, N6, N67. We need to discuss. Let us not discuss about this part right now. Once we come back to Auger, we will discuss. So first let us see how we can identify peaks. Just like X-ray diffraction, here we can identify peaks. So what is the general method? First is check peaks position and relative intensities of 2 or more peaks, both in case of XPS and Auger lines of an element. Checks the spin orbital splitting and the area ratios of PDF. First thing is the peak position and relative peak intensities or 2 or more peaks, that is what you should do. Second thing is the spin orbital splitting of our area ratios. So let us see the following things. Here it is basically the plot is showing for aluminum and silicon. You see this is coming for aluminum 2s, so we can actually know the peak position for 2s, what is the binding energy. So binding energy can be calculated. Aluminum 2p also, silicon 2s, silicon 2p, but it does not tell about what is the spin orbital splitting. Okay, so to do that, whether it is 2p half or 2p 3/2, one has to look into the area ratios. So as you can see, this is aluminum 2p, so therefore this will be 2p half, and this will be 2p 3/2, this will be 2p 3/2, this will be the small one will 2p 3/2. Silicon is also like that, one can detect. And if you scan the whole thing, there are many peaks. First thing is this, you can find oxygen, carbon, chlorine, silicon, nitrogen, all aluminum, sodium, so many peaks are observed. So that is what they done by just checking the peak positions. Second thing which you must know before even proceed further is what is the sampling depth, how much information is coming from what to the till what kind of depth of the sample. So normally this is again we use the same formula like X-rays. because it is axial penetration only, but electrons coming out after generation from the sample surface. So if we know the lambda I means for a particular element, inelastic mean free path of any element in a solid, we can do that. So for a electron intensity of I0 which is created inside the sample at a depth d below the surface, the intensity is attenuated according to the Beer-Lombard law. We have already discussed Beer-Lombard law in EV visible spectroscopy. So intensity Is which is coming on the surface is basically exponentially varies with dy lambda. So with a path length of 1 lambda, okay, that is 63% of the electrons are scattered. This is very clear when d equal to lambda is basically Is equal to I0 divided by E. So that means 1 by E of I0, that is equal to 63% of I0. That is what is said here. So therefore you must remember this formula. It is I0 exponential d by lambda, not lambda by d, okay. It is d by lambda. Lambda is the inelastic mean free path of an electron in a solid. That you must have knowledge first. You must have that. These are actually inelastic scattered electron, not elastic scattered electron, because these electrons are losing energies. So therefore one needs to know what is the mean free path of that. These are all available. Sampling depth is identified as the depth from which 95% of all photoelectrons are scattered by the time they reach the surface, correct. So it is the depth from which 95% of all the photoelectrons are scattered by the time they reach the surface. So more lambdas are in range of 1 to 3.5 nanometer for aluminum K radiation. So sampling depth at 3 lambda for XPS under this condition is about 3 to 10 nanometers. That's pretty small, about 100 Armstrong depth. You cannot get more than that. So if you have monolayer of 30 Armstrong, okay, this is how I actually get, this is the depth in nanometers, electromagnetic energy. As you see here, depth is very high, this is 100, this is 1000. As you say, this is depth is high, when you have binding energy is less, that's obvious, there will be more kinetic energy of electron. As the binding energy reduces, kinetic energy will be more, so it will be coming out. As the binding energy increases, it also decreases, but for a very high binding energies, again there is a increase. That is because of the effect which is different from the inelastic scattering. This is basically universal curve. So lambda actually depends on the kinetic energy of photoelectrons and the specific elements. This is that. So as specific element means what type of element it is, that is basically they dictates the binding energy. So now after knowing all these things, because you know sampling depth now, you know how the peaks to be identified, let us see how quantitative analysis can be done. Now in XPS instrument, measurements are accurate to the level of plus minus 10%. It is not very accurate, error is approximately 10%. The intensity which is coming out of sample surface is a function of Ni, sigma I, lambda I, k. What is Ni? Ni is the average atomic concentration of element I in the surface under analysis. That is what actually you want to measure. I, the intensity of electrons peak can be measured very easily. Ni is the average atomic concentration, that is our variable, or that is what is actually you want to measure. So sigma I is what? Photoelectron cross section. Basically is called Schofield factor expressed by any peak position P. Lambda I have already discussed is the inelastic mean free path of photoelectron, and K is all the other factors dumped in, like for quantitative assessment. You know EDS, how many other factors dumped in. In EDX actually there are factors like atomic number, difference, the fluorescence, all these factors are dumped in a particular parameter. Same way K has all the other factors. So basically, frankly speaking, intensity depends on the concentration of the element, photoelectron cross section of the element, and the inelastic mean free path of the photoelectron. These three factors. K is normally constant for any experiment. So as if you know if this is measurable, if you know these two parameters, we can calculate Ni. That is what is the quantification done. Now how to measure this I? That is what actually errors comes in, and that actually propagates into analysis. So if you look at this intensity by the kinetic energy pot, peak's shape is like this. This is not a typical X-ray diffraction peaks, little bit distorted. So one has to remove the background to calculate peak height. If you fit the background like this one, this is wrong. If you fit the background like this is also not best. The best one is to fit the background like this. That means background fitting is very important. So the standard measure on this sum instrument or full expression about the accuracy can be done if you have a standard, but reproducibility is always very high here for 2%. So worst cases in this measurement is this, best one is this, these are the middle. That is why actually the human error comes into picture, because it depends on how the measurement of the area depends on how you perceive the peak. Second important thing which one needs to consider for measurements of this quantum measurement is called transmission function, which is basically related to the detector efficiency. So this is nothing but detection efficiency of an electron energy analyzer, which is a function of electron energy. Transmission function depends on parameters of the electron energy analyzer such as pass energy. To give you an idea, if I have pass energy of 80 electron volts, and this is the the energies of the beam current, and this is done for gold after sputtering. As you see, the peak height here is this much, but when you have a pass energy of 20 electron volts, peak height is this much. So that means the peak height or the area under peaks get affected by the pass energy. Pass energy basically the energy which is used in the detector to energize to get to the electrons can be detected very easily. So this is what is basically dependent on the machine. So but you must have a knowledge about that. Normally these are all very fixed quantity for a particular setup, but one must know what is pass energy, how it can be controlled to get a good peak position, peak of that. Now what is Schofield cross section factor A? This can be calculated for each element from a scattering theory, basically for basically for aluminum and magnesium K alpha radiation, and similarly lambda I is varies with the kinetic energy of the photoelectron. It can be also estimated for universal curve, which I have told you. Universal curve is this one, this is the one, this is lambda I. This can be used to calculate all the lambda i's of different elements. Okay, so for a multi-element system, surface layer, which is normally the case, this is we can write down the constants of element Ni divided by Ni plus Nj plus K, or J, I, J, K are 3 elements. So this is how it is done. I divided by sigma I by lambda I divided by, this is the whole thing, whole divided by this one. This is for I, this is for J, this is for K. As you say, the factor which comes, capital K has been nullified because of the ratio taking. So that is how actually done. So I can also calculate Nj now. Nj is Nj divided by Ni plus Nj plus Nk. Similarly, Nk can be calculated. Let us see how these are done. Some examples. For oxide surface, that is oxygen metal atomic ratios determined for corresponding intensities. MgO palletized. One OS, O2s by metal is basically Mg here, 2p, ratio is this much, plus minus 10%. Okay. Now Al2O3 is also like that, SiO2 calculated, Cu2O. These are the different oxygen atoms, oxygen energy levels divided by metal energy levels, ratios. So these are the measurements actually tells us how quantitatively intensities can be correlated.